science lab, and today I'm going to be talking about a problem that I struggled with last night, specifically satisfying the Gauss-Bonnet law for an octant of the circle. So, this is actually not the best drawing, but let's say we have an octant of the unit sphere. I'm going to show that this octant satisfies the Gauss-Bonnet law, or Gauss-Bonnet theorem. What does the Gauss-Bonnet theorem say? Well, it says that the integral of the Gaussian curvature of any surfaces plus the integral of the geodesic curvature over the boundary of the surface is equal to 2 pi times the Euler characteristic. And of course this is the iconic vertices minus edges plus face. So, how do you calculate this for an octant? Well, first of all, you realize that the unit sphere has constant Gaussian curvature everywhere. The Gaussian curvature for a sphere is just 1 over r squared, but because it's a unit sphere, that just becomes 1 over 1 squared, which is just 1. Which means that this is just equal to the surface area. And the surface area for 1/8 of the sphere is logically just 1/8 of the total surface area. And of course, r is 1, so we can erase it here, which gives us 4 over 8 pi, or pi over 2. So this part becomes pi over 2. But what about this part? Well, that's when things get a little bit trickier, you see. How do you calculate this? Well, this is actually... What was it?
Oh, I did not use any mic today. It's fine. It's too late to use mic. I completely forgot.
Oh, right. I see. I'll just look it up by default. That's a curvature. Yeah, okay. Great. So geodesic curvature formula is okay. Just to make sure that's correct. Okay, yeah. Everything's totally correct. So, first of all, what does this mean? Well, this is just the curve we're looking at. And we're looking at 3 different versions of the quarter circle. The unit normal vector of the manifold, or the surface, along that curve, and the unit normal vector of the unit sphere, just x, y, z. And then the cross product of the tangent vector to the curve. So, what does that look like here? Well, quarter circle can be parametrized as just sine t cosine t. And so its double derivative would be minus sine t minus cosine t. This would just be equivalent to this, since the normal vector over the unit sphere is equivalent to the position vector. So that means you get gamma cross gamma prime, which gives you this cross this. Now you realize that both of these are in the xy plane, which means that their cross product has to be in the z direction somewhere. So if their cross product is in the z direction, then the other two components are going to be 0, and the z component is just going to be its magnitude. And its magnitude can just be measured as the product of these two magnitudes multiplied by sine of the angle between them. But these two are clearly perpendicular. This is just a 90-degree rotation of this, which means that the cross product's magnitude is 1 times sine pi over 2, which is also 1, which means that their cross product is 1. So that means you get this dot 0, 0, 1, and so you get what? Negative sine t, negative cosine t, 0 dot 0, 0, 1. That's a 0. Okay. Oh yeah. So the geodesic curvature is 0. And you can repeat this 3 times, but 3 times 0 is still 0. But you forgot one extra thing, because there's a discontinuity in the tangent vectors in these 3 junction points. So you have to add the sum of the 3 angles that you forgot about. Now I'm not going to show it, but it's pretty easy to prove that all of these 3 tangent vector discontinuities have an abrupt change of 90 degrees, or pi over 2. So that means this is just pi over 2 times 3, which gives you pi over 2 plus pi over 2 times 3 is 2 pi. Now what's the Euler characteristic of this thing? Well, you have 3 circular arcs. Well, you have 3 points, first of all. Vertices is 3. 3 circular arcs, 3 edges, 1 giant surface, 1 face. And that one surface is always continuous. So 3 points, 3 curves, because it doesn't count as 1 curve when there's discontinuities in the tangent vector, and then 1 continuous surface, 1 continuous face. Which gives you 3 minus 3 plus 1, or an Euler characteristic of 1. And when you plug that in, you see that these two are equivalent, so the Gauss-Bonnet law is satisfied. That's it. Thank you everybody for watching, and we'll see you in the next one.